there's this page, and then there's this folder that has a place we can put notes. We also have our AI transcription to help, but one of the things that I'd like to do with the notes is anything where we are trying to get to an agreement on something. Let's put that on the notes. We can look at it while we're talking about it and all know what it is that we're saying. So let me just copy the. My understanding is that we can all edit this at once in here if you can edit. There you go. So yeah, from here, we can do discussion. I will be quiet and listen and see what we all have to say. I think the things that I have to say about existing quantum compilers, I already told you. So here we'll count on the rest of you.
Else to say, I think the first thing I would say is the architecture diagram you showed at the very beginning of where you see the openQSE compiler.
Mm-hmm.
It's a very similar image to how Qiskit is designed, like almost exactly.
Yeah, that makes sense.
And so I mean, I can talk about Qiskit, but that is its role. It's designed to be that vendor agnostic layer that lets you glue together whatever input you want. Has a general battery. Why I'm holding these though. Has a generalized. It has its own IR for near-term circuits, but it's actually IR agnostic. There's an entire compiler framework in there that lets you work with multiple levels of IRs, which is something we're going to be using for fault tolerance. And then has a battery of passives that are generic. That work with different architectures, different types of systems. And then there's a backend system that lets the compiler generate code or do code gen equivalent, which in all of these systems tends to be honestly like JSON. At least how they're all built today, because they're all cloud connected or they use gRPC and it's JSON over that. And it's like, but that's the equivalent of code gen in all of these systems. But you can do whatever you want. There's a box for you to do that for each individual vendor.
Right. Have you seen cases where this sort of compilation infrastructure in Qiskit has been used with a different sort of high-level programming interface plugging into it?
Yeah, actually. So we have demos internally as we're looking towards fault tolerance. I was at a meeting in it about this earlier in the week. They're using blocking codings, which is a higher level abstract mathematical way of representing quantum algorithms. And they're using that blocking coding, which has its own IR, as they're doing optimizations using Qiskit's pass manager infrastructure to manage the blocking coding transformations, and then lowers it into a Qiskit circuit, performs optimizations, and then lowers that to hardware. So
starting from low encodings and above, when I think about fault tolerance, it makes me ask how much of what we already have will survive and where is it placed in the new? How much of the compilation techniques do we add to these new grouping techniques would be relatively untouched versus things?
So there's definitely a lot that's going to have to be done for new. So, I mean, on your earlier diagram, you were showing the fault tolerant pipeline. There were these boxes on the right that were
Just hold out.
Yeah.
Is it
This one, yeah. So like those right two boxes, like the runtime QEC operations and gates on physical qubits. In every architecture I know of, that is a domain of hardware. It has to happen at a time scale that there is software driving it, but it's the analogy I always use is it's like micro ops. And you don't program micro ops on your Intel CPU.
Yep.
And so, but like this bit, that's all new. There are ways you can skip Clifford and T. So you can do poly pushing directly without Clifford and T, get to PPRs and then go from there. But at the end of the day, like this stuff is new, and then some of the stuff we have to do for near term doesn't apply because we're going through this different path. But a lot of the more abstract optimizations and like reducing the circuit input, that's still universal because they're operating on a logical domain where you're divorced from the hardware level. The one thing I would caveat is there is a path where you can go from a higher level representation directly to that PPR, the poly product rotation. So that's like areas of research that we're looking at to go from a block encoding directly to PPC or something similar. And so like there are different paths to get to funnel in. But like when you look at the LLVM diagram, that's also a very good analogy where you can just funnel into a middle IR. So like for Qiskit, we're looking at actually this upcoming release, developing a new middle IR for fault tolerant systems, which would be different than the DAGs because the model of computation is just fundamentally different. It doesn't make sense to reuse it.
How is this IR of Qiskit like? Is it some standard LLVM or MLIR?
No, Qiskit does not use MLIR because while it's convenient looking at first to say, oh, there's an existing compiler infrastructure, we can reuse it. The advantages you get from LLVM, we found in practice, and we had internal tools written with it, did not yield any benefits for quantum. And it was basically like tying your hands. So like a concrete example is everyone ends up modeling qubits with memory semantics in LLVM because that's the only tool that's available to you for it. And it's just not a very natural fit. It's just the way you hack it. It's a very concrete example from working on it. But there are also huge issues with scalability, maintainability. And at the end of the day, the only infrastructure you really needed from LLVM is their pass manager, which is not that complicated. And so for Qiskit, we went with, okay, well, we can build our own pass manager system. That's pretty straightforward. And then the IR, it's IR agnostic, and we came up with, Qiskit uses more than one. There's the DAG circuit, which is the main one, but then individual passes have their own IRs. And then you can also build your own.
I agree that, okay, LLVM is a very low level, so it is not really expressible the needs of the quantum side. And but when we investigate the MLIR side, we can present in a lightning talk how we actually trying to use the MLIR for fault-tolerant quantum compiling. So there we see that it is highly expressible at a very high level, and we can actually adapt to the different domains and different different dialects, and that actually providing us the way to use the standard IR so that it can help to put more researchers to understand that IR, then start jumping on writing some optimizations, which can be vendor agnostic or something. So I see that these compiler IRs, something like standard, using standard IRs is enabling to actually provide some ecosystem for like LLVM kind of ecosystem to put more researchers to work on vendor agnostic process. So I would like to hear from IBM, okay, why are there any challenges faced from MLIR as well?
Many.
Okay, like
Tell us about it.
Well, I mean, the first one is when you're building production software, not research software, you have to keep up with LLVM. That is not a small task. LLVM moves very fast and changes things very frequently. And so when you start wanting to build a production stack on top of LLVM, you need a whole team of people just to keep up. That's the simplest one. But the next one is, like I said before, even with dialects and MLIR, it is all built around the needs of classical compiler. That is fundamentally different than this picture and the operations it's performing, the optimizations. So then what you have to do is write all of this in a framework that is not modeling the fundamental computation that you're performing. And that makes it inherently difficult. The example I cited before about everyone just using memory semantics because it's the closest to what you get with qubits is the most concise example I can come up with, but there are others.
Is that the case for Wake and Catalyst?
Yeah, they all
Use memory
they
semantics.
all use memory semantics to model qubits, which then limits the optimizations that you're able to do or leverage any of the built-in compiler features. Because you can't really do value semantics. It's qubits don't work. So memory is the only way they can make that work. And so like the more you look at it, the other one we had is just the performance was abysmal. Because LLVM is not designed to do this kind of stuff. So it was, and the scale of the circuits, like when you got above circuit size, it just was really slow. So
does it make sense to say that one possible task for this group is to have something that is a quantum semantics? Quantum semantics in the sense that memory semantics is the closest thing that can be done at that level because that's the tool that we have. Whether there's a generic way that we can find a new sort of semantics that works better in our favor.
I mean, that is what we did for the DAG circuit. If we do a data flow analysis and it captures semantics of qubits. The mistake we made in the DAG circuit is we also modeled classical information the same way. But that's also part of why we're moving to a new IR for fault tolerance.
Share more about what you're moving to, like what this IR will look like?
It's still under development. There should actually be a design doc published in the next week or two.
Okay.
I definitely agree that MLIR has some building kind of and maintaining versioning is also a tough thing. But LLVM, we actually resolve some of those problems by using containers or something like that to make use of this MLIR pass development. That actually enabled us we can stick to one version and then we can start building it. Building the compiler format, MLIR. Working directly on LLVM, yeah, it is full level. I definitely, there are several problems. Yeah. But MLIR, some of these problems got mitigated. I would like to bring to this committee also that, okay, we acknowledge that MLIR and LLVM have this kind of disadvantage from, and it's very hard to actually even write to passes. It requires still some expertise, but it will be even more harder to actually learn once vendor provided IR as well. Like it is not easy to say that, okay, one vendor may use their own IR, another vendor may use their another IR. Like Continuum is using this Hagar IR, right? So like that, everyone is defining the role IRs. So it will make it difficult to manage and adapt to all these IRs at one point of time. We recently worked on one very high-level IR, which is implemented in Julia. So we call it as a JLIR. It's a Julia level intermediate representation, which is natively defined in the Julia programming model. And okay, for giving some context, what is Julia? Julia is a very high level programming model, which is a hardware agnostic as well. Like you can actually write the kernels very customized for a underlying hardware like CPU, GPUs, or you can write a vendor agnostic kernels as well. So, and then it can nicely integrate with the other runtime systems as well. We see some gap that, okay, so if we have this intermediate representation, which is defined in this very high level programming model like Julia, and we found out that actually made it very simplified. Like I don't need to bother about compilation and build environments. And I can define the quantum dialects, and then I can actually write the optimization process on that. So we have worked on this MLIR-based fault tolerant quantum compiler, and I translated that whole code in JLIR, where with less than 8 times less code, I can achieve the same functionality. So, and it was more expressive because Julia provides the canonical representation where it is easy to represent any kind of expressions and write passes in very simplified manner. So combining this high-level programming model, it looks like it is essential even for quantum computing. So to make it more simplified, to enable to write this process like a compiler process for quantum computing.
Is this JLIR thing that you created or something?
Yeah, our group created that. Like we are in, it's a kind of effort of 2 groups in our section.
Mhm.
So we created this. We actually defined this IR in the Julia space, and we submitted a journal paper on this one. So once it is out, then we can make it public. Yeah.
And then
So-
are you feeling like that kind of approach is going better than using MLIR? Because you were doing both of these things.
We are having the MLIR as a main path for the Quantum Science Center project. But this is, we understand that there are some kind of shortfalls with the MLIR, like
Yeah.
as the, it is very difficult to actually build and provide some expertise on writing the process on MLIR. It is still a tough thing. Though it provides templates like how to write the process, it still makes it simplified, but it's still tough. We need to have some kind of expertise there. So we can simplify it by using some high-level programming models to write these compilers. So that's where the JLR came into picture.
Yes, I see. Whereas SDK is doing a very similar thing. They have Kirin, which is sort of philosophically neighboring MLIR, but very Python integrated. And I think that the question that I have about all of these is if everybody finds that it's easier to make their own thing, then we will not be able to share passes, right? What I want is not a shared IR. I want an ecosystem where we can share passes. And we need to get a shared IR to do that. So, well, debatable. But I think it would be worth a try, put it that way. But I mean, that makes me wonder if, like, is that it makes me wonder if it's too tied to the host programming language, then we won't be able to get enough behind a single. I often
We found that with Qiskit. Because Qiskit was originally Python only, and that became a limiter not only for performance but adoption from certain groups. That's part of why we introduced the C API, because C is far more universal. And even if, I mean, just demoed using it from Rust, and it's all through a C API, and that was.
do you use can you write passes in Rust? Is your Qiskit DAG?
So everything in Qiskit's core data model is written in Rust. And then we expose 2 public APIs to that Rust data model. One is C and one is Python. And you can write all of the passes that are in the default pass managers in Qiskit for targeting current devices. They're all written in Rust for performance reasons. And then you can extend the built-in pass managers however you like and write passes using either the Python or C API. We've done demos using Rust, Julia, Python, and pure C, that you just write a pass in whatever language you're comfortable with. You go through the same CFFI and it manipulates the data structure just the same way.
From this discussion, there seems to be a partition between compilation efforts in research and compilation efforts needed for operations, right? For actual performance in systems. they may be overlapping to some extent. However, one of the questions is that may be worth asking is how do we enable research that is closer to production, that doesn't break production, it brings things in a way that integrates more people's efforts, builds greater community, and makes these facilities, for example, the ones for the adult mentioned, serve as a kind of living lab for compilation research. That is, having these shared classes means that at some point, some of these classes are going to be, say, they gain more certainty of their quality or their utility. And so it has to be searchable somewhere. Saying, oh, for this project and this project, and this project, this pass was essential, or no, this was not applicable for X, Y, or Z. So
Yeah.
some way that we can catalog and categorize compiler research.
A lot of it out there.
But especially in connection with very large scientific applications, because at the end of the day, I think that one of the spirits of openQSE is the stage physics view integration, especially looking at openQSE. It's kind of the domain we haven't mapped. Some sort of testing and production, let's put it this way.
And that split is Qiskit's design philosophy for what it's worth. But we work in the research department, welding research. The idea is that you have performant core that's extensible and pluggable to enable research. And that's why the research papers I've published are built not into Qiskit originally. They're done as plugins on the side. A lot of research out there is built using this modular infrastructure. Found it to be very successful. To call out your PhD advisor, Robert Vilda's group, I know the group very well. They build on the same modular infrastructure, and all of their passes tend to be plugins for Qiskit for the same reason, because you can reuse everything that's built out of the box.
I did as well. So
Yeah.
So find examples of what are passes, examples of passes that we would like to be shared. So would also be nice to have examples to show. This is the pass we're doing X. This is how it shows up.
Yeah, absolutely. I mean, in the survey paper, what I'd like the survey paper to do is to enumerate the different IRs we see in different compilers, say something about them, and also say something about the passes we see in the different compilers. And we're looking for, kind of, is there commonality? Because if everybody has a completely different pass for everything, it's doing something totally different, then the argument that we can make some kind of community foundation that many people can build upon is wrong, right? So we need to identify commonality in the passes in the process of making the survey paper. It's completely reasonable to talk about that right now, but that's not something I know anything about.
Well, there's definitely overlap in the what the passes are doing. A lot of them go about it differently. So like two that I've spent a lot of time looking, Qiskit obviously, but also TCAT from Quantinia. You can look at the structure of how everything is built. They're very similar. And the passes, they go about things in slightly different ways, but the end goal is the same. And in fact, TCAT has started using passes from Qiskit, and we had experiments with using TCAT passes in Qiskit as well, like going the reverse way.
Sort of a side question, but had you looked at Hugger?
I've looked at Hugger
of doing these things. Like, would you be able to characterize how it's different or similar to the DAG circuit?
So Hugger, from my impression, is much more concentrated on expressive dynamic circuits, and it's optimized to be able to efficiently express the classical control flow embedded within the coherence time of a circuit. And that honestly makes sense for Quantinium because ions are really, really slow. And so I have a colleague whose PhD was in ions, and he said you can do dynamic circuits by plugging a laptop in over serial, and you'd be fine. But that's what they were concentrating on, is like having a combined IR representation that was very rich for the classical, but still quantum first.
Right. And this gets to something that I think we have to wrestle with, because nobody else in the openQSE community is going to wrestle. Like in none of the other working groups are going to wrestle with that. And it's specifically for these dynamic things. For example, the capability to do a loop, or capability to do conditionals and things. What is the level of functionality we can expect, portability for among different QPUs? And one of the areas that I have a lot of question marks is what happens to that when we add in error correction. But to my understanding, I think like with IBM stuff, you do allow loops. So these sort of very dynamic things, like you could allow literally any Python function to be called while the qubits are doing something, but having the ability to do a loop and add two numbers and have conditionals and things like that, it seems like there's some kind of agreement among the community, at least if we ignore fault tolerant for a moment, that those things are needed. So that makes me curious about, well, why would Hugger need to be different from Qiskit DAG if you need control flow and that's all dynamic circuits?
It's about richness of expression, I think. So DAG circuit was very much like a static circuit design originally, and we kind of grafted on the control flow on top of it. And so it's possible to do it, but it's not the most ergonomic to do like classical optimization. But for the model we came with for it, though, was in practice, even with like the ion systems that are using Qiskit, the expressivity of the classical side is you're very limited in what you can do because of the strict timing requirements. You can't have unbound loops in a circuit under any circumstance, because everything has to be statically timed to control either your lasers or your microwave pulses or whatever the actual physical mechanism for the qubit is. And so it didn't matter in practice for the DAG circuit. I think Quantinuum is trying to push more on using the slowness of ions as an advantage and trying to do more than others in this space are. And so I think that's probably why I don't know why they did Hugger, but that would be my guess.
It says something about the future FTQC compilation infrastructure, that some things should be marked for pre-compilation, for example, faster architectures versus something that could be done more just in time. Is there an option that could try to rebalance those metrics?
Can you say that again?
Given that there's these architectures with different time requirements, that tends to be solved some of the classical world with that's the reason we have instruction prediction in a microprocessor. If there's compilation just in time, or even microprogramming, offers in microprogramming environments where you can specify things in advance that have been pre-computed, estimating what will happen or knowing what will happen because of specifications. But if you have lower time frames, then you can do just in time, and that translates from the pre-compiled bus to a just-in-time bus, or just-in-time generation. I wonder if that balance can be achieved and still express something in a general way, then parametrically to have a few flags that say, oh, I'm working with ions, I can afford the time, or I'm working with superconducting. I really need this to be divided by the time. Trigger architectural components.
I have a feeling that Hugger is just in time compiled in practice, but I don't know for sure. Just looking at it, that's the vibe I get.
That's where my division comes from, because looking at the two differences, it is a difference about time and a difference about availability of resources, especially in time as a resource.
Yeah. I'm allowed to say. The thing, so I don't know much about Quantinuum's internal architecture, so I can't really talk to that. But the thing I think where the limits still are on all of this is even with time, there are hard execution constraints. Like it is not a general purpose processor because you are like in Qiskit, we define different domains of execution and timescale. And so like when we're talking about dynamic circuits, we call that real time, which is within the coherence time of a single circuit execution. There's a whole other domain called near time, which is running on like a classical co-processing system. In IBM, we call that the IBM runtime. Qiskit runtime for terrible branding reasons. And there that's a processor. That's just a CPU. You can run whatever you want on that. But that has to be distinct from the real time because operating within the coherence time of the circuit really does limit what you can do because you can't have anything unbounded, even with fault tolerance, because fault tolerance is not fault free. And so I personally expect always this split to exist, even long term, because you can't deal with unbounded execution unless your fault tolerance is so amazing and your hardware is so great that like the time scales are longer than a human lifespan, which I can't foresee. I mean, I guess the other side is you can just generate random noise and not have a productive execution, but that's
Stopping point there. I wanted to ask about all the product rotations and programs. From what I've learned in looking at it, I can't see how to do, for example, a loop or a conditional gate or measurement at all in this representation. And I hypothesize it will be possible to extend polyproduct rotations to do some of those things, but I don't know what that looks like or if it basically becomes ineffective as an optimization technique and a way to represent the logical operations by the time we add those. So I wanted to know if those of you in the room know the answers to those questions, or if they're completely research areas, or what.
and this is all still very active research areas, like how to do this kind of compilation, what capabilities are. I'll say one of the things we're looking at, like I said, the middle IR we're going to be working on for Qiskit is PBC-like. It's not pure PBC, it's PBC, other things added to it. The plan is not in the first version, but in future versions to grow it such that it becomes a basic block and control flow graph. And that's basically the equivalent to how we're going to do something similar to outlining to reduce binary size. If there are repeated blocks, we can outline that into a for loop or something like that. That's the primary motivation I think we have for looking at looping.
Right. So I would imagine that when you have a big enough processor, the implication of all of that, one implication of all of that is that you probably want to have multiple threads, in quotes, of basic blocks running on the quantum processor on different qubits, because you'll want to have different classical reactions to their data, and you won't, like if they're, for example, doing repeat until success or something, like they're not all going to be behaving the same way. So it wouldn't be possible to put them all in, sort of run them as a fleet on the same basic blocks. Sort of a, maybe that's true, maybe that's not, but that's something I'm curious about. If you think about it that way or some other way.
I mean, it really depends on input program, but also a large degree of it comes down to the underlying architecture of the hardware. Because there are certain operations which might end up being sync points, like there could be, magic state factories that basically become a sync point. If you're operating in this model where it's like, oh, you've got parallel execution, so you've got your different modules,
Yes.
logical memories that like are all working in parallel, and then all of a sudden you do this thing and everything has to wait until you're done processing it.
Yes.
There are architects, so it like
Sort of depends on how you put it all together.
it depends on how you put it all together. There are all sorts of different ways. I mean, it's all theoretical at this point too. There are all of these different theories for how you can construct different fault-tolerant computer architectures. That kind of indicates a lot about what level of parallelism you could exploit or not.
Right.
But then it also comes based on like what the algorithmic input is. If you have 200 logical qubits, and the algorithm assumes deep entanglement between all 200 logical qubits, there's not much parallelism to exploit there.
Well, it would have to be a very, literally what I have in this diagram to do it as a basic block, because all of the pictures in here assume that everything's measured at the end. You definitely wouldn't want that in a basic block.
We're trying to combine two things. One is the hardware, whether that supports the corresponding conditional gating hardware. And from the programming point of view, and like a high level programming models like Qiskit or some other kind of programming like openQSE, and it may not be having that, but it may be extended to happen. So, but from IAP side, it should be like whether we are targeting for the hardware, or it can be even for simulators as well. So, but it is a kind of a programmable feature and IR feature, whether it supports it, having both quantum specific semantics along with some classical semantics, something for the conditional the loops or something like that. So, and then it will be about lowering step, like, okay, so based on what is my target hardware, where the hardware has that support, then we can call that corresponding interfaces of that hardware to generate into the IR and then apply those optimizations to convert into D2 gates corresponding operations. So if it is simulator, then suppose if the QLAC suppose that kind of a conditional gates of the looping, right? So then I may actually lower it in different way for the simulator purpose. So IR can provide that kind of flexibility based on what is my lowering target.
Right.
Different pictures that are popping up in how to build an FTQC system. It seems like a task that we might need to do is to have an inventory of all those new emerging models and to figure out what are the minimum common denominators for population that we can assume from those.
The net takeaway we have had from that is that at a fundamental level, it all looks very similar to the lattice surgery from the Latinsky paper, that they all end up being PBC-like at some level, and then it's the constraints on which you play this game. I mean, he's specifically focused on surface codes, but if you look at QLDPC codes, fundamentally it's the same way. It's just different constraints and how you map from the PBC representation. That's why I said the middle IR we're focused on for fault tolerance is PBC based at its core, with extra stuff for ease of optimization and efficiency and implementation of passes.
Yeah.
Because if you just limit yourself to the operational model of PBC, then you might end up tying your hands when it comes to writing things efficiently in middle optimization.
Well, this kind of gets to a question that's sort of more about our survey paper, which is, do we need to have some amount of survey of planned QEC strategies? Because really the IR at in a lot of the compilation is representing what we are going to do on top of the QSE. And so that error correcting code is kind of forming our instruction set and kinds of operations we're going to do.
Yeah.
I mean, do you think that paper should talk about some of those?
It might make sense. I mean, if you're looking at a survey paper, talk about like active research, it's definitely worth talking about. If you're looking at the ecosystem of packages that are out there, it's still very nascent.
Right. But it would be defining kind of our requirements about what would our IR need to be able to do, right? And obviously at IBM, you've been doing that for superconducting systems, or at least systems that don't have trapped ions or neutral atoms or moving qubits, right?
Qiskit supports all of those use cases. The target is agnostic to modality.
Do you think your upcoming FTQC representation will be a good fit for those moving qubit?
The goal is to have it be supported for all of these different architectures that are being proposed. That's one of the design tenets of Qiskit is that it is agnostic to any vendor implementation or hardware modality. It just has to be a universal quantum system. That's both, like, we are trying to build an open ecosystem around compilers with Qiskit. That's part of it, but it's also like, if you want the selfish business reason, this is all active research. We don't know what the future is going to be. We don't want to tie our hands. We're committed to superconducting as a business right now, but wasn't to just buy HRL.
That question. But maybe with what I understood.
Maybe that's
well, we have a few minutes left. I wanted to spend a little bit of time with everyone by talking about terminal. I've had some specific things I wanted to ask about, just among the people here, if we can come to some conclusion on some of these terms. Like, did you like the way that I was distinguishing compiler IRs and interchange formats, or do you think we should use other terms? Starting point?
matches my mental model, where especially I often think of IR as more in memory. It can have a language or serialization one-to-one, but it's first order in memory construct of compiler, while interchange formats are languages or serialization formats that are standard.
Any other comments?
I agree.
We're happy with those terms? Okay. Yes, we're happy with the terms. The people in the room right now, everyone else is not in the room, so they don't get to. Okay. And then this one's sort of stupid, but is MLIR an IR? I think it is not. Because it's a framework for defining IRs, so it can't self be an IRs.
Meant an IR.
Yeah, it comes with, in the package, there are some standard dialects. Those are IRs, but anyway, you want to argue about it?
If you want to talk like MLIR as a library, then it may not be IR, but it is giving you the utilities to define your custom IR.
Absolutely, yes.
So yeah, what you're defining is the IR for the quantum or less any other neuromorphic or any other domain.
Okay, sounds like that's sort of a terminology level thing. It sounds like we're comfortable with no, but it allows you to make IRs. Okay, here's the one that I'm expecting the most fireworks about.
I would like to add one more point.
Oh, okay.
from the point of writing the parsers, right, it defines standardized interfaces.
Yeah.
How we can access those operations, those are standard.
Uh-huh.
So from the IR point of view, it is just not about having the dialects. It is about the interfaces to access those operations. So then it is still in IR.
Yeah, that's interesting. I mean, that makes it like maybe it's halfway to what I would call an IR.
Yeah, like instead of hard coding the dialects, here we have the flexibility to define our own dialects, then we can write the same way of writing the past template.
Yeah, but you still can't share a pass. Like if I have a pass in my compiler and you have a pass in your compiler and they do the same thing, we can't share it unless we're working on the same dialect.
Then we need an adapter there to share it. Like we can convert like from one dialect to another dialect.
Right, but that's the same as converting between IRs. And
Yes, same by converting.
anyway, I want to ask this other sort of stupid terminology
Where's
question.
transpile? It's my fault. No, not my fault personally.
You're like, I'm done with that transpile.
It was, when I joined the team, it was already picked, and there are internal political reasons why it's not called compiler.
Okay, that's fine. So my personal opinion, just because I'm talking right now, I'll share is we should just use compile for everything. It's a general term, and we don't need to. Like when we say what the component does, for example, it is translating from QEC patch operations into logical qubit primitives, right? Then we should have more concrete words, maybe even some nice short words. But for the general thing of we're translating quantum circuits, I just leave it at compile unless I have a better reason. But anyway, so
In Qiskit, when I give presentations, I always start with the preface. In Qiskit, our compiler is called the transpiler for historical reasons, and I will use transpile and compile interchangeably, whether I'm talking about the thing doing something versus the act it's doing.
all right, Matt says don't use transpile. Does anybody else want to use transpile?
I think small suggestion too, but
Yes.
we prefer the elements of the final lowering process, the each runtimes, that we refer to that as hardware synthesis and not compilation. It organizes better the mental model of what is happening, and also it allows separating the symbolic manipulation that a compiler does versus the actual instruction streaming that needs to happen, which is tied to real-time constraints.
Well, something around this. So, I mean, my kind of understanding is like transpile would be a good word or would be a good process word. I mean, today's things which we are doing in around like this rack. But when we will go more to the like abstract notions as Sir has told. So I think, I mean, to my understanding, my level of understanding, I feel like that time compiler sounds more general and more like more inclusive rather than like just mapping or.
That's a good point, right? Just even if we like the term transpile, it won't apply when we're applying it, like when we're doing more FQC things.
Transpile is a term which has been used to translate the program from one programming model to another programming.
That's what it actually
It's-
is. That's exactly.
Translating
Yeah, it's not.
So if I could let everyone in on a secret, I had a side project writing COBOL bindings as an April Fool's joke that got blocked by corporate marketing. But one of the lines in the blog post I had written is Qiskit now with true transpilation, because the best open source COBOL compiler is a transpiler that transpiles COBOL to C and then runs GCC. And
Okay.
So Matthew, can I ask something to like have some because of some reasons, you call it as transpiler, and it has started like, I mean, now almost everyone in the quantum community calls it transpiler. Like,
Yeah, because
because of
Qiskit's the biggest player in
yeah.
compilation space, so it's.
Can we ask like what were like, I mean, the things which kind of influence the word transparent? I mean, I'm just interested to.
The justification that we're facing was that it was translating from one circuit representation to another, and that wasn't lowering or doing compilation. It was the outward facing message. There were internal reasons why they didn't want to call it compiler. I can't really talk more than that, but that premise that it was not lowering was a lot. It does. Like, you can look at the representation of Qiskit's circuit input, and I view the quantum circuit as like an input IR, not a programming language. That is highly abstract. You can define the equivalent of your own dialect for like any abstract operation that you want to perform in any abstract program, and it will lower it into gates. And the hardware circuit is a very different thing than what the input is. And so it is a compiler. There's no question when you can say, here's the evolution of a Hamiltonian in mathematical terms, run this on the system, and it outputs something that runs on the actual hardware. That's a compiler in any sense of the word. And that's what Qiskit lets you do.
Great. Well, I think we just completely agreed on some terms. So I think the one that we were the least close to total agreement on was whether or not MLIR is an IR, but that doesn't matter. So, and now it's noon and we're done until the afternoon session. I have no idea which of you will be back in the afternoon. I hope to see as many of you as possible. If you can't come in the afternoon, those are coming this morning. Among other things, I am hoping we'll get somebody from Quantinuum in the afternoon. So it might be interesting to talk about here in the afternoon. It might be interesting to talk about the difference between the IRs a little bit. Anyway, thanks everybody. And I have no idea what we're doing now. I said, lunch or something. It's eating.